Okay, Assalamualaikum and a very good day to all. So let's continue with second part. In second part, we are going to discuss the real life applications where we are going to apply the second law of thermodynamics, the efficiency of Carnot engine, and then the application is going to be covered with the heat engine, refrigerator or air conditioner, and the last one going to be heat pump. Okay, so let's start. Okay, so before we discuss further with the real life applications of second law of thermodynamics, definitely we need to understand what does it mean by second law of thermodynamics. Before this, we discussed about zero law, where zero law is about thermal equilibrium. Okay, and then we discussed about first law. It's about conservations of energy. And now we are going to discuss about the second law of thermodynamics. So second law of thermodynamics basically state that the heat is spontaneously flow from hot region to cold region, or we can actually say it from high temperature to low temperature. So for second law of thermodynamics, it's agreed that heat definitely can flow from high temperature to low temperature. What about if we say in vice versa, means that the low temperature can flow to the high temperature? Yes, but you need to have some work done over there. That one we are going to discuss for applications of refrigerator and heat pump. Now we are going to discuss about the true second law of thermodynamics. Okay, so let's start now. Okay, so here we have heat engine, or we call it as a Carnot engine. Okay, so basically heat engine and Carnot engine is the one of the real life applications that obeys the second law of thermodynamics and second law of thermodynamics. However, for this one, there's going to be disobey the second law of thermodynamics. Okay, so basically you are going to have a heat engine. Okay, heat engine, or we can put it as a steam engine. Okay, so this engine is mostly used in automobile, cars, or any ship. Okay, is considered as a heat engine. So what does it mean by heat engine? So heat engine is a device that convert heat from outside. So heat from outside, it can be any source. It can be solar energy, it can be mechanical energy, it can be nuclear energy. So here we are going to have a higher energy, QH, okay, hot, atau we can call it as hot or higher, Q hot. And then what happen is this energy are going to be transferred, part of it as a mechanical work, and a part of it going to be the Q out, or we can actually as a hot energy, cold energy. Okay, so means we can actually say that the cold energy is basically a waste. Okay, so in heat engine, we want to make sure, example like a car, your energy, they're going to be delivered by oil. Okay, so the oil going to provide you some energy, Q hot or Q high. And what happen is, if you want to move the car, is going to be as a mechanical work. Okay, and some of it going to be reject as the waste, which is in the cold energy, or we can actually say as a low energy. Okay, temperature here, T hot, and T cold here, we call as the operating temperature. Okay, so our mission here, heat engine, we want to make sure that we can actually provide like most part of it to go for the mechanical work, and just little part of it go to the heat, go to the waste, which is as a Q cold or Q low. Okay, so that's the reason why we have this one diagram. When you actually draw the simple diagram of this one, you have a Q hot, which is the operating temperature is at T hot. You taken this heat, you receive this heat from higher temperature source like solar energy, oil furnace, or nuclear reactor. And what happen is you are going to transfer most part of it as a mechanical work, which is we are going to put W here, work done. And some of it we are going to waste, reject it as a waste, remaining waste heat at the Q cold, and the operating temperature going to be T cold. Okay, so this heat engine are going to operate on a cycle, which means that they are going back to initial state. It's going to keep going to keep repeating all over again. So it means that it's going to initial states, going to receive the heat from outside and then transfer to the work done, and then the remaining going to be the Q cold, and what happens is going to keep repeating the same steps. So this is what we call as the heat engine. Okay, so the heat engine here, based on the formula itself, heat engine, okay, I'm going to show you here. So we receive heat from outside. At this time, the operating temperature is going to be T hot. Okay, and then we want to make sure that the most part of it go as a mechanical work to move something. Okay, so example, your car, you want to move your car, so mostly we are going to make sure that the oil over there is mostly used to move your car. Okay, and then a part of it, and small part of it, we want to make sure that is goes as a waste, or here we can call it as a Q cold. Okay, and the operating temperature here is T cold. Okay, so when we come with the formula, we have the efficiency, which is represented by E, or you can actually put it as like that. Okay, so this both symbol is basically for efficiency. Efficiency state that output over input. Okay, so means that your main output here, you want to make sure that you move the car. That's the reason why here you are going to get W, and your input is the one that need to make sure that this engine can be operated. Definitely Q hot. Okay, so that's how you get the formula for efficiency, work done over QH, and the efficiency, it doesn't have to be multiplied by 100%. It's up to you, and there's no unit for the efficiency. Okay, because this one joule and joule cancel out, then you get nothing. Okay, so it must be true if I said that here, based on this diagram. Okay, based on this diagram, it must be true if I said that the Q hot is basically going to be separated into most of it as a work done and also as a Q cold. Okay, this one is basically a conservation of energy. Okay, first law of thermodynamics. Okay, so we rearrange the equations, then we are going to get W equals to Q hot minus Q cold. So what happened here is we are going to put it inside this formula. Okay, so we are going to get efficiency equals to Q hot minus Q cold over Q hot, which also same as 1 minus Q cold over Q hot. So Q over there is basically heat. Okay, so make sure that you use only informations that represent heat. Okay, that's about heat engine. Okay, then we have a Carnot engine. Okay, Carnot engine is basically a most perfect engine in the world. A most perfect engine in the world. Okay, which means that, example, if like heat engine, maybe you can transfer your heat that you receive, maybe only 50% of it, or maybe 60% of it. But when it comes to the Carnot engine, it's going to transfer as mechanical work, maybe 99%, and only 1% going to delivered as a waste. Okay, the Carnot engine. That's why we call as the idealized engine, and their Carnot engine going to be irreversible engine. Okay, like I mentioned before, what does it mean by reversible? Reversible means there's no engine, there's no heat loss. Okay, maybe there's going to be there's no heat loss, there's no energy loss, or maybe just 1% of energy loss. Okay, that's why we call as a most perfect engine. But this one only basically theory. The heat engine is the real life application. The Carnot engine, the Carnot heat engine is basically only about theory. Okay, so what does it mean by Carnot engine? Okay, I'm going to explain further with the Carnot engine how it works. Okay, but here, if we want to use the formula, the Carnot engine state that when you use the formula like the previous one, okay, the efficiency equals to Q hot minus Q cold over Q hot. The Carnot engine state that if you use temperature, you are going to get the same efficiency as you use heat. Okay, so the Carnot engine state that if you use heat, which is efficiency here, temperature hot minus temperature cold over temperature hot, which means that this efficiency same as the efficiency when you use the formula heat. Yes. Okay. So means that when the question state Carnot engine or idealized engine or the most efficient engine, then you can actually use the temperature. Okay, you can only use temperature at this part only. Okay, so it can be this formula, or it can be efficiency equals to 1 minus T cold over T hot. So what happens is the efficiency that you use if you use temperature will be the same for efficiency if you use the heat. Okay, okay, that's what Carnot engine state, because it's the most perfect engine. That's the reason why it said that if you use the operating temperature, you are going to get the same efficiency if you use the heat one. Okay, okay. So this one is the Carnot heat engine. Okay, Carnot means perfect. Okay. So what does it mean? So what does it mean by Carnot? How Carnot engine works? Okay. So or this one I already explained to you. So means that you can only, okay, this is basically also the symbol for efficiency. Okay, so you can actually use this formula or this formula for Carnot engine. If the question state heat engine, then you need to use this formula. If the question state reversible engine or the most perfect engine or idealized engine, definitely is represent Carnot engine. Okay, so how it works, how Carnot cycle works. Okay, so Carnot cycle works with 4 steps. That's what we call as a 4-stroke cycle. Okay, so it's going to have 2 adiabatic and it's going to have 2 isothermal. Okay, so what does it mean by adiabatic and isothermal? Okay, let's recall back. Adiabatic means no heat flow into or out of the system. No heat flow into or out of the system. Okay, and the isothermal means constant temperature, or you need to maintain temperature at that particular situations. Okay, so Carnot cycle is idealized and reversible. Okay, so let's start with the how it works. Okay, so basically this is a very simple diagram of how Carnot engine works. Okay, so this thing going to be in cycle, which means that it's going to return back to the initial state and it's going to start all over again. Okay, so I'm going to start from here, but I'm going to talk a little bit from here. Okay, because it's related so much. Okay, so first thing first, at the isothermal expansion, okay, so I need to explain for adiabatic compression a little bit. Okay, so for adiabatic, it means that there's no heat into or out of the system. So basically this is the piston. So basically what happened here, the piston is basically compress the gas. Okay, compress the gas. So what happened is when it compress, the volume going to be decreased. What happened to the pressure? Definitely going to be increased. And what happened to the temperature? Temperature going to be increased. So means that at this particular time is going to change from T low to T high because of this compression. Okay, so it goes back to here. Okay, so when at this particular time the temperature is will be low to high, and at this particular situation the temperature going to be higher. But what happened is when it goes higher, okay, when the temperature goes higher, so it means that the molecule inside here going to push the pistons upward. Okay, so when the molecule push the pistons upward, what happened is the internal energy of the molecule going to be decreases. Why? The internal energy going to be decreased. What? Why? Because as you can see that when the molecule push the pistons, it means that they use the work to push the pistons. So what happened is the internal energy going to be decreased. And when the internal energy decrease, what happened to the temperature is going to be decreased. But at this particular time, you need to make sure that you maintain your high temperature. So how to maintain that higher temperature? Yes, definitely you need to add the heat. Okay. So when you add heat, what happen is your temperature from lower going to maintain at the higher temperature. Okay, and then zip is going to change into adiabatic expansion. At this particular time, there's no more heat added to the system. There's no more heat out of the system. Okay, so means that at this particular time, the molecule here are going to push the pistons with their own internal energy without any help from outside. So when it push further, what happen is the same thing like I mentioned before. The internal energy are going to be used as work to push the pistons up. So what happen is from higher temperature is going to be low temperature. Okay, because most of the work done are going to use to push the pistons. So the internal energy are going to be decreases. What happen to the temperature is going to be low. Okay, so when it goes low, what happened to the piston is going to move downward. So it's going to change to the isothermal compression. Okay, so when it goes to the isothermal compressions, okay, at this particular time is going to be the piston is going to be at this time. Okay, so what happened when the pistons move downward? Okay, so it's going to decrease the volume. What happened to the pressure is going to be increased. What happened to the temperature is going to be increased. So what happened is the molecule over there are going to receive the energy from the height because of this pressure. So what happened is going to push pistons upward. But at this particular time, you want to maintain the lower temperature. And the problem is not right now you have higher temperature. So how to do that? Yes, you need to remove the heat. Okay, you need to remove the heat. Okay, once you remove the heat, what happened to the temperature is going to change into low temperature. Okay, because at this particular time you need to maintain your lower temperature. That's the reason why you need to remove the heat. Okay, so what happens when you remove the heat is going to be lower temperature. So at this particular time it's going to change back into adiabatic compression, where at this particular time the piston is going to be downward. And then what happens is going to give pressure to the molecule gas here. So what happens is the temperature over there going to be increased back. So from lower to higher. Okay, so as you can see that here there will be no loss of energy, conservation of energy. Okay, and then it's going to keep repeating all over again from isothermal expansion to adiabatic expansion, isothermal compression to adiabatic compression. Okay, that's how it works for Carnot engine, a most perfect engine. Okay. Okay, so basically in front of you is the what we call as a real diagram of what happened in the car itself. So basically the pistons over there is the one that are going to connect to the crankshaft. So it means that right now you are trying to move or to do some mechanical works to the crankshaft, and that's the reason why you have this 4-stroke cycle. So the 4-stroke cycle basically start from here to here. Okay, so when they said the both valve close, it means that at this particular time is the adiabatic compression. Okay, so I think maybe some of you think how heat added to the system. Okay, so this is what happened in the real car engines. Okay, so at this particular time the adiabatic compressions, it means that it's going at this particular time the pistons, it means that it goes upward to give some pressure to the gas air mixture from carburetor. So what happened is because of this pressure, what happened is it's going to change here, going to be isothermal expansion. Okay, so when they give some pressure, what happens is going to ignite the mixture of gas and air. So at this particular time you need to add a heat. Add a heat here is basically you give some pressure to the gas and mixture, so it's going to cause a spark. Okay, so what happens is piston going to be pushed upward. Okay, so when the mixture when the pistons goes upward, and then it's going to change back into what we call as a adiabatic expansion, which means that there will be no more heat into or added to the systems. Okay, so at this particular time when the adiabatic expansions, it means that it's going to change the higher temperature into low temperature. Okay, but now they are going to change back into isothermal isothermal compressions. Okay, so when it does, okay, so isothermal compression, it means that at this particular time you need to maintain the low temperature. However, during adiabatic expansions, the pistons, there's no more heat added to the system. There's no more help from outside. So what happened is, the pistons are going to be upward, so it's going to cause some pressure to the gas. Volume decreases, temperature increases, but at this particular time you need to maintain back the isothermal the temperature low. So what happens is, this one is going to be Q out. It means that you are going to remove the heat. So you are going to remove the heat means that you are going to exhaust the valve, which is the valve going to be open. So this is what we call as a 4-stroke cycle, which is the real life applications of the car engine. Okay, so this is the graph of the Carnot engine. So you have two adiabatic and then you have the two isothermal. So there's going to be alternate adiabatic isothermal expansions, and then it goes to adiabatic expansions, then it goes to isothermal compressions, and then it goes to adiabatic compression. And then you can see that the flow of the Carnot engine going to be reversible. There will be no heat, there will be no loss of energy, and at the same time it's going to be cycle. Okay, so you can see that in front of you, this is how it works for the 4-stroke cycle. Okay, so basically what happened is, we want to move the crankshaft in rotational motion. That's the reason why we need to have two isothermal and two adiabatic expansion. Okay, two adiabatic. Okay, so basically here is going to be this one going to be when heat added to the system. Okay, this is basically Q added to the systems. And then what happened here, when it moved the shaft, what happened is the internal energy is going to be decreases. And then if you want to maintain back the lower temperature at this particular time, you need to make sure that you have a Q out. Okay, so basically it's going to rotate the shaft, and that's the reason why we use the 4-stroke cycle. Okay, so basically what happened here, I already explained it to you. I already put the notes over here for you to understand, but it's not going to be so much detail. I'm not talking here about the molecule, but I think you are going to get that understanding based on the explanation before. Okay, so you can go through for this one. Okay, so basically we have a Carnot cycle. That's why we have a reversible isothermal, reversible adiabatic. Okay, and this is the continuous part of the explanations that I have discussed with you before. Okay, and then this is basically the conclusions of the formula that we are going to use for the heat engine and for the Carnot engine. So basically Carnot means perfect. It can basically Carnot not only for the heat engine, it can be Carnot refrigerator, which we are going to discuss later. But it means that Carnot here represent this one, where the efficiency itself is the efficiency you can actually get for the temperature for the Carnot engine. But if the question state heat engine, you are going to use only heat formula for you to find the efficiency. Okay, so here I already explained about the Carnot engine. Basically there's a way for you to derive why the efficiency of heat will be the same as the efficiency for temperature, but it's pretty long, and I think it's not that important for you to know the derivations. Plus there's a certain part that you didn't learn, so once you learn in thermodynamics, which in your future study, definitely you are going to fully understand what does it mean, why this formula, why you are going to get this kind of formula. Okay, so that's basically the same thing. Okay, so this is the things that I already mentioned before. Okay, and then what happened here, if you have power, you can actually use efficiency with the power as your formula, where you can see that power is basically work done over time. So if example I give it to you, power instead of heat, you actually use efficiency is power output divided by the power input. Okay, so you are going to get Q output over time, which is this is going to be no, this is not Q, is going to be a work done. Work done is because you the output is going to be the mechanical works, and the divide by the input that you need to put is the Q hot over time. And that's how you use the formula. Okay, so let's start with the refrigerator or air conditioner. So basically for both device, they are going to share the same applications, where here they are going to disobey the second law of thermodynamics. Okay, second law of thermodynamics state that heat spontaneously flow from hot region to cold region. However, for the refrigerator, is going to be vice versa, where the cold temperature or low temperature going to move to the higher temperature. It is logic, yes. It's logic if you have some work done to the cold temperature over there, then it can actually move or transfer from low to high. Okay, so what happened is when you have this simple diagram, okay, Q low, okay, you are going to receive some heat low from outside, which means here is going to be nitrogen gas, okay. And then what happen is if this gas want to transfer from cold to hot, what happen is going to receive some work done. Here in refrigerator, the work done is provided by the motor itself. So it means that it's going to give some kinetic energy to the molecule to transfer from cold to hot. So it's going to be from motor. And what happening is going to transfer the heat out. So it means that your waste going to be Q hot, which is at the higher temperature, higher operating temperature, and this one going to be at lower operating temperature. Oh, I forget. You can use low or cold, is basically the same thing, and you can use high or hot because it's the same thing. Okay. So refrigerator and air conditioners share the same system. Okay. So how does a refrigerator works? If you see something like this, you can imagine how a refrigerator works. Okay, so let's proceed to the next one. Okay, so here is a refrigerator. So we have two parts, which we have the internal part, which this is going to be the inside part, and this is going to be the outside part. Okay, so the inside part is basically where your food actually where you place your food over there. So we are going to start from here. So at this particular time, you have a low pressure liquid. So what happened is when this low pressure liquid move inside the refrigerator, at the same time is going to absorb heat from food. Okay, so what happened when it absorbs heat from food? Okay, and what happens is going to change from liquid to gas. Okay, it's going to change from liquid to gas, but at the lower pressure. Okay, so the reason why it's going to absorb the heat because it wants to provide a cool temperature to your food. Okay, so when it changed from liquid to gas, but at this time your gas going to be at lower pressure, okay, at the lower temperature. So that's the reason why we need to use a compressor motor, which is basically this is the work done to provide the energy to the lower pressure gas and then turn that into high pressure gas. Okay, high pressure gas. So what happens is when it compress, it's going to provide some energy to the lower pressure gas, change it into high pressure gas, so it's going to move outside the refrigerator. So at this particular time, it is going to remove the heat to the environment. Okay, that's why you have a QH over here, okay, to remove heat from the environment, and then it's going to turn from the from the high pressure gas into what? Into high pressure liquid. And that's the reason that you need to have the expansion valve to change from liquid, high pressure liquid to low pressure liquid. Okay, yes, and that is going to be in cycles, and that's how it works. Okay, so that's why when you change into this diagram, okay, so basically the Q low is what happened, means that the Q low is going to be provided by the nitrogen gas. So at this particular time, you are going to have a low pressure liquid. Okay, low pressure liquid, and then what happens is you are going to absorb some heat from the food, And then when the low pressure liquid, and then you are going to change into low pressure gas. Okay, so what happened is when they have a low pressure gas, that's the reason why we need to use a compressor to change to high pressure gas. Okay, at the outside part of the refrigerator is going to remove the heat, and that's the reason why when you touch the back of your refrigerator, you can feel there's some hot gas coming out from your refrigerator, and this is this is what happened. Okay, so it's going to remove the heat, and then it's going to turn back into low pressure. It's going to turn into high pressure liquid. Okay, so and that's the reason why you need to have the expansion valve to change back into low pressure liquid. Okay, and then it's going to be in cycle. Okay, so basically this is the what the things happen here. Okay, so you need to have a compressor, you need to have the expansion to change the high pressure liquid in the expansion basically to change the high pressure liquid into low pressure liquid, and the compressor is basically to change low pressure gas to the high pressure gas. Okay, so in front of you we have okay, so here I'm already explained to you of basically this is the explanations on how the refrigerator works. Okay, so you can actually go through this thing. Okay, and then now we are going to come up with the formula for the refrigerator or air conditioner. Okay, so basically what happened here is we have this a very simple system, which is Q cool from the operating temperature of T cool, and then it's going to transfer the heat from low to hot, but definitely they need to have a work done, and then it's going to transfer the Q hot outside the refrigerator. Okay, so here for the refrigerator, we are not going to use the efficiency. We are going to use the COP, which is stand for the coefficients of performance. Okay, COP, the formula going to be what you want to achieve in this device, what you want to achieve in this system. So basically, the refrigerator you want to reduce the heat inside your food and lower the temperature of it. So that's the reason why you are going to get the main objective of the refrigerator is to Q cool. And then what you need to put into to make sure that this device is going to work, definitely you need to put a work done. Okay, so it must be true if I state that the Q cold combine the word with the work done, then you are going to have a Q hot, right? Okay, so the same thing, you rearrange the formula, so you are going to get here work done equals to Q cold over minus the Q hot minus the Q cold, sorry. Okay, and then you put it into this formula, so you are going to get the COP, the coefficient of the performance, which is Q cold over Q hot minus Q cold. Okay, so this if the question state ideal or Carnot refrigerator, okay, if the question state ideal or Carnot refrigerator or air conditioner, so means that is the most perfect refrigerator in the world, which is basically not exist. Okay, so you can use the coefficient of performance using the temperature. You can use the COP with the temperature, so means that here going to change COP equals to T cold over T hot minus T cold. Okay, only at this part you can change into temperature, not for this part and not for this part. Okay, Okay, so basically what happened here is if the question state Carnot refrigerator or the ideal refrigerator or reversible refrigerator, it means that the COP you obtain for the temperature are going to be the same the COP as you obtain from the heat. Okay. Okay, so basically this is the one that I already mentioned before. Okay, so this is basically the formula. Please do not use efficiency. You are going to use COP, the coefficient of performance, which are going to move the heat from lower temperature to higher temperature with the help of work done, which is come from motor. Okay. Okay, so basically this is difference between heat engine and also the refrigerator. Okay, so what happened here is for the heat engine, you move from Q hot, you taken heat from outside, like from nuclear, from mechanical works, and then you want to transfer most part of it as a work done, mechanical works, okay, and then you transfer some of it as a waste, which is at the Q cold, okay. But for the refrigerator is vice versa from the heat engine. You taken heat from nitrogen gas, okay, so disobey the second law of thermodynamics, but you can make it to the higher temperature with the help of the work done, and then you can you can transfer the heat, or you can actually reject the heat outside the refrigerator, which is at the Q hot. Okay, there's a difference between these two systems. Okay. Okay, so what about heat pump? Okay, heat pump and what we call as a refrigerator, basically the system is almost the same, but the objective here is different. Okay, for the heat pump, the main reason that you use the heat pump is to heat up your house. Okay, to heat up your house. Okay, so means that here you are going to take heat from outside during winter, which is heat outside is basically cold, and then what happens is you are going to transfer to inside with the help of work done. Okay, so you can actually see that the system looks the same, but the formula going to be different because the objective is different. Okay, so if I draw here is basically you taken heat from outside, which is at the lower temperature, lower temperature, okay, and then you transfer the heat with the help of the work done, and then you transfer the heat into the inside of your house at higher temperature or Q hot. Okay, but here the formula going to be different. You are going to still use the COP, but the main objective here is you want to heat up your house. That's the reason why you're going to get Q hot. Okay, but what you need to put into the system to make sure it works, definitely work done. So basically here the Q cold, when you combine with the work done, you are going to transfer heat inside the house, which is the Q hot. So you are going to get W equals to Q hot minus Q cold. Put it into this formula, so you are going to get the COP equals to the Q hot over Q hot minus Q cold. Okay, so the difference is at the upper part of the formula, for the heat pump is going to be Q hot, but for the refrigerator is going to be Q cold. Okay, so if the question state Carnot heat pumps, means that at this part only, the COP you obtain from the heat is basically the same as the COP you obtain from the temperature. Okay, so that's how it works, and that's the formula for the heat pump. Okay, so basically for the heat engine, it's transferred from high temperature to lower temperature. Okay, but for the refrigerator or the heat pump, is basically you extracting heat from the cold part and then you deliver it to the hot body. Okay, and mostly for the heat engine, there's not the coefficient performance, sorry, supposedly it should be efficiency here, should be less than 1, but the refrigerator for the COP should be equal, greater, or less than 1. Okay, so let's start with the first example of the questions. Here, I forget to remind you, when it comes to temperature, make sure that you always change into Kelvin, which means that you need to add up with the 273. you can actually use 273 or 273.5. Okay, and then make sure that for the work done, always be in joule. Okay, always be in joule. Example, if I give it to you calorie, you need to change from calorie to joule, which means that for one calorie equivalent to 4.184 joule, or is same as 1 kilocalorie equivalent to 4.184 kilojoule. This one you need to remember. Okay, so basically here the question state that the steam engine. So when the question state the steam engine, it means that is basically a heat engine, one of the example of the heat engine. Okay, so designed to accept the steam at 300 degrees Celsius. So when it comes to accept, means that the 300 degrees Celsius is the T hot. Okay, and exhaust this steam at 100 degrees Celsius. So this is going to be T cold. What it is maximum possible efficiency? So example, if the question state for the temperature, it means that this steam engine is the Carnot engine. It means that the most perfect steam engine in the world. Okay, so means that you need to use the formula efficiency equals to 1 minus T cold over T hot, or you can actually put low or high, basically the same thing. So 1 minus, make sure that you change into Kelvin first. So it's going to be 100 plus 273 over 300 plus 273. So you are going to get this formula. It doesn't necessarily you need to multiply by 100%. You can just give your answer in 0.35 only. Okay, that's how you answer the questions. This is very simple, very easy. Okay, let's move forward to the next one. Okay, so for these questions, without looking at the answer, I'm going to explain it to you. A Carnot type engine is designed to operate between 480 Kelvin and 300 Kelvin. Okay, a Carnot type engine, which is the most perfect engine. Okay, assuming that the engine actually produce 1.2 kilojoule of mechanical energy per kilocalorie of heat absorbed. Compare the actual efficiency. Actual efficiency, it means that the heat engine, and the theoretical maximum efficiency, which is the Carnot engine. So the question asks you to compare between theory and the real efficiency. Okay, so let's start with the Carnot, with the theory efficiency, with the Carnot engine. Okay, so efficiency, they already give you the 480 Kelvin and 300 Kelvin. Based on the number itself, you can actually detect which one going to be higher, which one going to be lower. So I'm going to use the efficiency equals to 1 minus T cold over T hot. So you are going to get 1 minus 300 over 480. So you are going to get 0.375. Okay, easy. Okay, however, for the actual efficiency, it means that the heat engine, you cannot use temperature. Okay, please take note, when the question state actual or heat engine, you are not allowed to use the temperature, because temperature only can be used for the Carnot, which is the most efficient one. Okay, so it means that for this formula, the question give it to you only 1.2 kilojoule, but there's a hidden meaning here. Okay, there's a hidden meaning where 1.2 kilojoule of mechanical energy. So what does it mean? Mechanical energy equivalent to the mechanical work. So basically this is work done. Okay, mechanical energy per kilocalorie of heat absorbed. Heat absorbed is what? Q hot. So means that 1.2 kilojoule of mechanical. So the formula is efficiency for the Carnot will be work over Q hot. So it means that 1.2 kilojoule of mechanical energy, which is work, per divided 1 kilocalorie of heat absorbed. So heat absorbed with the Q hot. So it means that you need to write 1.2 is basically work kilojoule per kilocalorie, per 1 kilocalorie of heat absorbed. Okay, so you need to be read the questions carefully, because there's a hidden meanings over there. And like I stated before, kilocalorie you need to change into kilojoule first. Okay, so it's going to be efficiency equals to 1.2 kilojoule. 1 kilocal is equivalent to 4.1. 1 kilocal equals to 4.184 kilojoule. So you are going to get 4.184 kilojoules. So you are going to get answer is 0.287 for the efficiency. Okay, so here if the question state 1.2 kilojoule of mechanical energy per 2 kilocalorie, so means that you need to put it here too. But right now the question just state per kilocalorie. That's the reason why I put it here as a 1 kilocalorie. Okay, that's how you read the questions for the thermodynamics part. Okay, you need to be extra careful. Okay, let's move to the next part. Okay, so next is the question for the heat pump. Okay, is to be used to heat a building during the winter. The building is to be maintained at 21 degrees Celsius at all time. The building is estimated to be losing heat. Okay, based on our simple diagram. Okay, that's the reason why for the thermodynamics, I encourage students to draw your simple diagram for you to understand the system. And then you can actually identify whether it's going to be for the Q hot, for the Q cold, or something like that. Okay. Okay. So for this heat pump means that you are going to take heat from cold part. Cold part, and then you are going to transfer it with the help of the work done. Transfer it as the Q hot or T hot, and T hot is basically the operating temperature. So the building is estimated to be losing heat at the rate of 135,000 kilojoule per hour rate. This is basically power. Okay, when the outside temperature drops to -5 degrees Celsius, determine the minimum power required to drive the heat pump. So basically the one that responsible to drive the heat pump is work done. Okay, but the question asks you about power, which means that the work done over time is going to be power. Okay, so how to do this question? Okay, now the building is to be maintained at 21 degrees Celsius, which is basically inside building. And the outside temperature is dropped to -5 degrees Celsius. So right now, the question asks you to find the work over time, which is the rate work done. Okay. So like I mentioned before, for the heat engine, you can actually use power also for the COP, which means that the COP going to be P output over P input. Okay. Which means that the output in the heat power and in the heat pump is going to be Q hot over time. Okay. And then the input here, to drive the heat pump is going to be work done over time. Okay, now we already have the informations for for this one. Okay, because the building is estimated to be losing heat. So basically what happened is, for the building to estimated to be losing heat means that you transfer the heat into your house. Okay, right? And then, however, and then the question asks you to find this one, okay, but you don't have the COP. Okay, you need to find the COP first. Okay, so the COP, now you can actually see that the COP can be calculated from what? From the temperature. So basically this is the heat pump with the Carnot engine. Very perfect one. Okay, so means that I'm going to find the COP first using the temperature, which means that for the heat pump is going to be COP equals to T hot over T hot minus T cold, which means that, okay, make sure that you change into Kelvin. So the T hot going to be 21 plus 273 divided by the T hot minus T cold. 21 plus 273 minus -5 plus 273. So you are going to get your efficiency is, so you are going to get 11.3. Okay, you don't have to multiply by 100%. Okay, it's not necessarily to multiply by 100%. Okay, once you get the COP, basically you are going to get the power, the minimum power required to drive the heat pump. Okay, so means that you are going to get the work done over here. So means that using back the formula, so we are going to get the COP. Okay, I write the formula first. The Q hot over time. This is basically power. Okay, you don't have to worry because you are not given the time here. Don't worry about that. Okay, over work done over time. Okay, so means that we need to find the work done over time here. So we are going to get work done over time equals to the Q hot over time over COP. Okay, so now I have 135,000 kilojoule per hour. So 135,000, you need to change first into kilojoule per second. Okay, so kilo is power of 3, joule per hour. So joule per hour, so you need to have the conversion unit here. So 1 hour is equivalent to 3,600 seconds. So the COP here is 11.3. Okay, so you are going to get your answer is, so you are going to get 3319, and the unit is going to be it's going to be joule per seconds, or you can actually change it into 3.319 kilojoule per second. So basically this is power to drive the heat pump for this outside temperature. Okay, so for the question for the thermodynamics, you need to like read questions carefully, okay, and extract all the information given. And the tricks is make sure that when you extract, you put it like the symbol. This one is for what? This one is for Q hot of minus over T. Okay, and then to drive the heat pump is what? Is basically work done over time. Okay, yes, it's much better because when you extract and then you assign the symbol for it, it's much easy for you to put it inside your formula. Okay, okay, so this is basically the same steps. Okay, I already showed you before. Okay, I already provide you with the 7 questions of the thermodynamics. Combinations of heat engine, Carnot engine, refrigerator, and also heat pump. Please do it. Okay, we have these questions 1 and 2, 3 and 4. This question also, and the last one going to be these questions. We are going to discuss each questions number 1 until 7 during online teaching, but please try to do it by yourself first. Okay, and I'm going to explain to you how to extract the info and how to use the info inside your formula. Okay, so that's all for now for last chapter. So please make sure that you study the thermodynamics, make sure that you understand the theory. Please do not rely only on the formula. You are going to easily get confused because the formula itself, how to use it, you need to understand the theory first, and then you can actually easily use the formula. Okay, so that's all for now. So I'm going to see you during online teaching. Okay, so goodbye and assalamualaikum.